Okay, welcome to another lesson in organic chemistry. My name's Dr. Hill, and I'm going to be talking to you today about the physical properties of the alkanes. Remember, alkanes are a homologous series. They're all saturated hydrocarbons. In this case, we're going to talk about single straight chain alkanes, carbons 1, 2, 3, 4, maybe a little bit further than 8, just for the purposes of talking about their physical properties. Now, what do I mean by physical properties? Well, in general, I'm talking about whether the thing is going to be a gas, a liquid, or a solid. Remember that when things are very cold, they tend to be solids when they don't have much energy, because the particles get kind of locked in place. They don't have enough energy from the temperature to make them break free of their neighbours. They're very strongly attached to their neighbours in a solid. When I give them more energy, I start overcoming these intermolecular forces because the particles start moving faster, and then they start breaking apart, and with more and more energy, i.e. heat, I can make them move around each other. I can make them change their position in relation to other particles or other molecules in the substance. And that means I've turned my solid into a liquid, and the particles can all move around each other. And as I keep adding energy, remember, as I add energy, each individual particle is going to move faster. It's going to take up more space. The liquid will start expanding in volume until I reach the point where it boils. And when it boils, what's essentially happening is that the particles have now got so much energy that they overcome the intermolecular forces and they break away. And they can start flying around, and they can start mixing with other atoms that are, at the same energy level, and those that will, because the liquid has become a gas. Okay, so we go solid, locked together. You can't change your neighbor. Liquid, they're still in one substance, and a liquid will fill any vessel that you put it in, and it will fill the bottom of any vessel that you put it in. And so the molecules are still attracted to each other, and the energy that they have hasn't overcome that attraction. And then eventually, when I add more and more energy, I make the particles move faster and faster and faster, and eventually they can overcome that attraction that they have to each other, and they can break away and start making friends with all other sorts of particles in gas mixtures. Okay? So the amount of intermolecular attraction that there is between particles or between molecules in a substance is determined by a couple of things. One, its size. The bigger particles are, the more intermolecular forces there are, so they tend to be more attracted to each other, and they're harder to pull apart. They can even get tangled up with very long organic molecules. And so if we take something like this is octane. It's possible that octane can get tangled up with lots of other octanes, and it makes it much harder to pull them apart. The other thing that can increase intermolecular forces is particular parts of molecules that might create little electromagnetic attraction to other particles. This is what we call dipoles and polar areas of molecules. In the alkanes, of course, we don't have any of those. The carbon-hydrogen bond is pretty non-polar in general, and it doesn't cause any electromagnetic attraction or electrostatic attraction to anything else around it. There are some organic molecules that do have electrostatic attraction within the intermolecular system, so we'll look at those later. So what happens? So, well, we've got our methane here. It's a small molecule. It doesn't take much energy to make this shake loose and become a liquid. So it becomes a liquid at a very low temperature. That means that its melting point from solid to liquid, its melting point is a very low temperature, something like minus 180 degrees Celsius. And not very far after that, it boils, because it doesn't take much more energy to get these things to fly apart from each other. They're very small, there's only 4 atoms in it, and they don't have particular attraction apart from just very simple intermolecular attraction. And so if I add even a little bit more temperature, the individual atoms become They vibrate so much that they pull away from each other and become a gas. So when I encounter methane at room temperature, which is 20 degrees Celsius, it's a gas. It's a colorless gas, and it's... let's look at this fella here. This is propane. It's got three carbons in it. Again, the melting point of this is well below 0 degrees Celsius. The boiling point of this is well below 0 degrees Celsius. And when I encounter this at room temperature, it's also a gas. This fella over here, though, because it's much bigger, it's a bigger molecule. It's harder to pull these apart when they're all tangled up together in a solid or in a liquid. Its melting point is substantially higher than these, but it does melt well below 0 degrees Celsius. And so when I encounter this at room temperature, it is a liquid. And it doesn't take a great deal of heating to turn it into a gas. So let's see, we've got a trend, haven't we? We've got a trend. As our alkanes increase in carbon chain length, their melting point goes up and their boiling point goes up. So let's have a look at a table here on the internet. I just picked one out at random. I'm not going to draw it on the desk. And so let's switch across to that. And as we can see here, if we look at the carbons, we've got the carbons down here. The number of carbons is the number down the left. And methane has a melting point of minus 180 degrees, 82.5 degrees Celsius, and a boiling point of minus 161.6 degrees Celsius. So we're going to encounter this as a gas. It's not until the boiling point goes past 20 degrees room temperature that we're going to see a liquid. Okay, so let's go down to that one. We've got it here. Here's one here. Pentane is 36.1 degrees Celsius boiling point. So at room temperature at 20 degrees, that's going to be a liquid. I have to heat it up another 16 degrees to get it to boil and turn into a gas. So generally I'm going to encounter pentane as a liquid. All right, so all of these here are going to be liquids, but now we don't need to look at this to find out what's going to be a liquid at room temperature. We need to look at our melting point, because it's the melting point that turns things from a solid into a liquid. So what's the last one of these these alkanes that I'm going to see as a liquid at room temperature, and which one is going to become a solid? So let's crawl down the page here and see the numbers. So here we got positive temperatures here. So at roughly 18 degrees, which is 2 degrees lower than room temperature, hexadecane is going to be just about a solid, is going to be just about a liquid at room temperature, and heptadecane is going to be just about a solid at 20 degrees Celsius. I need to add 1 degree to turn that into a liquid to get it to melt. All right, when I get down to octadecane, I need to be at 29 degrees to get it to melt. It's the melting point, remember? And so I'm going to encounter octadecane as a solid at room temperature. All right, and all of these will be solids at room temperature. And in order to turn them into gas, I now need to supply a fair bit of energy. But alkanes, of course, are relatively simple molecules. There's no particular intermolecular forces apart from just the general attraction of molecules to other molecules and possibly tangling effects as they get bigger and bigger and bigger. So the physical properties, just remember, as we increase in carbon number, the melting point increases and the boiling point increases, and it's a relatively stable increase. All right, so that's the physical properties, at least the melting point and boiling point of hydrocarbons, of the alkanes, sorted out. So hopefully I've done that in 10 minutes, and you can look these numbers up anytime you like in a table on the internet. You can get the tables anywhere. So I'm going to say goodbye, and hopefully that's all done in 10 minutes.